So remember how I said this is going to play a big part in the next section. Let f be continuous on the closed interval and differentiable on the open interval from a to b. Then there exists a point c in a to b such that this follows. So remember, this formula is what we practiced in the last section, but we're really focused on this idea of continuity and differentiability. And the reason why is because, remember, if you have an interval from a to b, and let's just say we have these 2 points, and then there's a secant line between those 2 points, right? The slope of that secant line, somewhere, no matter how you draw the function, somewhere in there, and it could happen multiple times, but somewhere in there, the instantaneous rate of change is going to equal the same as the slope of this line. And you could see that happens like right there, that happens right there. It happens a couple times in this example. And so what happens if this were to not be continuous? If it wasn't continuous, there's a possibility of it failing. You could have something where this, like from here, it just goes straight up, and then from there, just like straight down. It never has a point where it has that same slope. You could also have, if it's not differentiable, like if you have a corner, that also runs that same risk. You can have a line going into another line like that and never have the curve have the same slope as this secant line here. So that's why it has to be both differentiable and continuous. Now remember, in order for it to be differentiable, it has to be continuous. So if a problem says that the function's differentiable, that implies that it's also continuous. But it's not so the other way around. If I tell you a function's continuous, it could be continuous and have a corner. But if I tell you a function's differentiable, that means at every spot it has to be continuous. So just by it being differentiable, it will cover the continuity. Just by it being continuous does not cover it being differentiable. Okay, so what does this have to do with this assignment? We got these great ones coming back. So we're going to look at their justification. We're looking for that establishment of continuity. We're looking for that establishment of differentiability. We're also looking to make sure that average rate of change equals that instantaneous rate of change, or that goal that we have. So the table gives selected values of the differentiable function f. So it tells us that f is differentiable, and remember that because it's differentiable means that it's also continuous. Remember, that's our justification, though we have to take a look at the justification that they're doing in this problem. So below is Leo's attempt to write a formal justification for the fact that there exists a value c in this interval in which the derivative, the instantaneous rate of change, equals 1. So we want to find where that average rate of change equals 1. So between 7 and 8, does the average rate of change equal 1? And does he establish the continuity and differentiability? So let's look. His justification, he does the average rate of change, finds that it's 1. So he's saying, hey, because of that, f prime of c must equal that average rate of change of 1 somewhere in the interval. You know, if you were to look at that definition of f of b minus f of a over b minus a, it would be true. But does he establish that differentiability and continuity? No, he doesn't. So look at this answer, B. No, Leo did not establish the average rate of change of f is equal to 1. No, that's not exactly what he did wrong. No, Leo should have mentioned that f is differentiable, which would then cover the continuity, but he didn't do that. It would be nice if you were to do the proof, you would say it's differentiable, but also because of that, you would mention it's also continuous. So look at this one. Finn's justification, we're given that h is differentiable. Since differentiability implies continuity, you know h is both differentiable and continuous. Great, he established that. So according to the mean value theorem, h prime of x equals -2. Well, hang on. He never established this part. He never showed the average rate of change was -2. We need that part. So no, he didn't establish that. He needs that. He needs to show that h prime of c equals that f of, or h of 0 minus h of -2 over -2 minus, or 0 minus -2, my bad. But he needs to show that. It might be true, we could do this problem, it might be true from -2 to 0. If you do that average rate of change, it might work out. Okay, for the next one, we're going to go ahead and justify it. So the table gives us a differentiable function g. Make sure it's differentiable. You know, right here, If they gave you the table and they didn't establish this differentiability, we can't assume that a table is differentiable, that the function's differentiable or continuous. It has to be told. But since it's differentiable, it covers the continuity, so we're good. Can we use it to justify from negative 18 to negative 16 that our derivative is 50? So let's go ahead and take a look. So negative 18 to negative 16. So we'll do g of negative 16 minus g of negative 18 over negative 16 minus negative 18. So g of negative 16 is 30 minus negative 20 over, that's going to be 2. Negative 16 plus 18 is 2. So that gives us 50 over 2, which is 25. So no, since the average rate of change of g over the interval is not equal to 50. If it was, we would be good. Everything's covered. For this last one, you just do the same idea. You would just run through g of 5 minus g of 3 over 5 minus 3. So g of 5 would be 2 to the 5th power, which would be 32 minus 8 over 5 minus 3. 32 minus 8 is 24 over 2, which is 12. Not exactly equal to that 16, is it? So once again, we run into that same problem. But if it was 16, we would say, yes, we are good.